In this lesson, we're continuing our exploration of the area of composite figures. Now we're looking at shaded regions. So a shaded region could be used to identify really any shape. It could be for regular and irregular shapes. As you see on the left, we have something similar to what you've already practiced. But on the right, you see that if we were to cut that into a bunch of smaller shapes, that would be pretty confusing. So instead, we're going to find the area of the larger shape and then subtract the area of the smaller shape. So let's take a look at this irregular shape. So again, we can break this up into many simple shapes, or we could take the area of the larger rectangle and then subtract the area of the parallelogram that's not shaded. In other words, it's missing. So the area of a rectangle, we apply the formula, base times height, and we get an area for the rectangle of 558 millimeters squared. The area of the parallelogram, again, base times height, and we find that to have an area of 78 millimeters squared. So now to find the area of the shaded region, we're going to subtract. We take the area of the rectangle, the shaded region, we subtract the area that is not shaded, which is the parallelogram, and we get an area for the shaded region only of 480 millimeters squared. Now looking in this example, we see we could break this into two triangles. However, we weren't given any dimensions that would allow us to do this. So we have to find the area of the larger trapezoid and then subtract the area of the triangle that is not shaded. In other words, that's the piece that's missing. So the area of the trapezoid, again applying the formula, 1/2 of the two bases added times the height. Substitute in what we know, and we have an area of the trapezoid of 195 feet squared. The area of the triangle, that's the section that's missing or not shaded. Formula, 1/2 base times height, and we have an area of 60 feet squared. So now the area of the shaded region, again, we take the area of the trapezoid, we subtract the area of the triangle, and we get the area of the shaded region to be 135 feet squared. Now this one's not much more complicated, but take a look at the dimensions, particularly right here on the bottom. Okay, so to find the base of the triangle, well, let's actually first look at the rectangle. That's pretty easy. We just see that we have a base and a height, 20 and then 12 inches. But now if we look at the triangle, we see that we're not given the dimension of the base. However, we're given the dimensions of the two sections right next to it on either side. So to find the base of the rectangle, we're going to have to subtract those two 8-inch lengths from the overall length as we see in the top of the rectangle, which is 20. So after subtracting, we see we now have the base for the non-shaded triangle to be 4 inches. From there, it's just like any of the others. We find the area of the rectangle using base times height to be 240 inches squared. The area of the triangle, again, 1/2 base times height using the base that we just calculated, and we have an area of 12 inches squared. So to find the area of the shaded region, just as before, we're going to subtract area of rectangle minus area of triangle, and we get 226 inches squared. Now, how about if we include some circles? So we can still subtract the unshaded from the shaded region. In this case, we have a larger circle, and then unshaded is a square. But you have to be careful with these kind of dimensions. You'll notice in the larger picture, the overall picture, the radius was given inside the square. It might be hard to recognize that that actually belongs to the circle. Also, the side of the square, it's given outside the circle. It's pointing to the edges of the square, but sometimes it's a little difficult to see. So with these types of problems, when you have circles involved, you have to be very careful and really just use some detective work to figure out what the radius might be. So in this case, we now have the area of the circle. We have a radius of 6 meters. We apply the formula. And we have an area for the circle of 113.04 meters squared. The area of the square formula is just one of the sides squared. So 8.5 squared gives us 72.25 meters squared. So the area of the shaded region, again, we're going to take the area of the circle minus the area of the square, and we have 40.79 meters squared. Another instance where you have to be careful. Here, you have to think a little bit outside the box. So to get the radius, you have to notice the edges of the circle here, 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 and here. All 4 of those edges touch the edges of the square. So to find the square, that's pretty easy. We're just going to take that outside square, the larger square. Notice that each of the sides is 8 meters. Now for the circle, because this side is 18 meters, that means from this point to this point, going right down the middle, this is also 18 meters. And if we wanted to, we could also notice that because this is 18 meters, then this distance is also 18 meters. But no matter how you slice it, we now know that we have the distance across the center of the circle to be 18 meters. But again, we have to be careful when we're looking at area. Area of the square, again, very simple. Take one of the sides and square it. So we have 18 squared, 324 meters squared. For the circle, although we've figured out that the distance across the center is 18 meters, that's the diameter. So to use the formula, we're going to need the radius. The radius is just half of that diameter. So when we substitute in our radius, it is 9 for 9 meters. So the area of the circle is now 254.34 meters squared. So the area of the shaded region, just as before, take the area of the square, subtract the area of the circle, and we get 69.66 meters squared. Time to practice.